The main topic of this lecture is to figure out the optimal choice in a two-goods model. Therefore, let's quickly review the two-goods model. We obviously have two goods, good 1 and good 2. We consider a single point in time and a single individual. This individual must decide on how much to consume of each good. We use x1 and x2 to denote the consumption of good 1 and good 2 respectively. x1 and x2 are greater than or equal to 0 and goods are infinitely divisible. Each good has a price, P1 for good 1 and P2 for good 2, both strictly positive. The individual has an income M greater than 0 to spend on these goods. The equation of the budget line is an equation that the bundle x1, x2 must satisfy if the cost of the bundle is to be precisely equal to income. The consumer has a weak preference relation, which is a total order. So present the consumer with any two bundles and she will tell you if she weakly prefers the first to the second or not. This is the standard setup of the two goods model. In some cases, we will make additional assumptions. In some cases, we will assume that preferences can be represented by a utility function, and in such cases, we will often assume that this utility function is smooth. In some cases, we will assume that preferences are well behaved, that is, strictly monotonic and strictly convex. And in some cases, we will add both of these assumptions. So let's define what we mean by optimal choice. We have a two goods model with totally ordered weak preferences. No additional assumptions are imposed. Remember that the budget set was the collection of all bundles that the consumer could afford given prices and income. The cost of the bundle is less than or equal to her income. A bundle in the budget set which has the nice property that it is weakly preferred to any other bundle in the budget set will be called an optimal bundle, an optimal choice, or a demand bundle. An optimal bundle will be denoted by x1 star, x2 star. No affordable bundle can be strictly preferred to an optimal bundle. As long as the budget set is not empty, there must be at least one optimal bundle due to the fact that preferences are totally ordered. However, we may have many or even an infinite number of optimal bundles. If we have several optimal bundles, then the consumer must be indifferent between all of them. Optimal bundles are classified into two groups. If an optimal bundle does not contain any amount of good 1 or good 2, then we say that the bundle is a boundary bundle or a boundary solution. If the optimal choice contains a strictly positive amount of each good, then we say that it is an interior solution. Since we do not allow negative quantities, the x1 axis and the x2 axis becomes the boundary between allowed bundles in the first quadrant and forbidden bundles in the remaining quadrants. The distinction between these two is made for mathematical reasons, as we will soon see. Here is a picture demonstrating a typical case where we have a unique interior optimal bundle. We have a budget line, the collection of all bundles satisfying the budget equation. The budget set is the triangle. I have drawn 3 indifference curves, but there is an infinite number of them in the first quadrant, never touching each other. Each indifference curve is strictly decreasing and convex. Better bundles are located on indifference curves up and to the right. The optimal bundle is the bundle where one of the indifference curves touches the budget line. We are not able to afford any bundle on a better indifference curve as they are strictly above and to the right of the budget line. Any other bundle in the budget set cannot be optimal since it will be located on an indifference curve which is below and to the left of our touching one. In this example, note that the slope of the budget line is equal to the slope of the indifference curve at the optimal bundle. This will turn out to be an important characterization of an internal optimal bundle. Let's look at the graph when we have a boundary solution. We have the budget line and indifference curves. In this case, the optimal bundle is located on the x1 axis and the optimal bundle contains 0 units of good 2, x2 star is equal to 0. It's clear that this is indeed the optimal bundle. Any other bundle in the budget set will be located on an indifference curve that is below and to the left of the optimal one. Here is the other case. The budget line, indifference curves, and the optimal bundle is now on the x2 axis with x1 star equal to 0. From a mathematical perspective, the important point is that the slope of the budget line is no longer equal to the slope of the indifference curve at the optimal bundle.